Okay, good morning everybody. As always, first question, do you have questions? Is there anything we should discuss? If I remember it right, we made it until the last slide of the first presentation, so this was the last slide we had. I gave you a short explanation what unobservability, anonymity, unlinkability is. It wasn't really formal definitions. It's more that you get a kind of impression or feeling what properties we want to describe. And then if we are talking about particular security measures, these names will reappear. And of course, we have to discuss the particular meaning then in this context. But you should have an overall feeling what anonymity is, what unobservability is, and what unlinkability is. So, next is exercises. Did you do some exercises, and do you want to discuss about them? Who did do exercises and has questions or remarks, or is prepared to present something on the blackboard?
I have a question about number 3.
So 5, 3.
Yes.
Yes. Okay. Okay.
I'm not sure about my answer. In my opinion, I think we should do encryption first. No. Yeah, we should do encoding first, for tolerance, encoding first and then encryption, because I think maybe if we do the other way around, sorry, my opinion is do encryption first and the tolerance encoding later. Because
Okay, maybe we have to spell out what first means. So let's assume we have some source of messages, okay? So we do some kind of encoding of a message, for example, ASCII or any kind of coding scheme, okay? So this probably happens first. So first, second, third means we are considering the steps from the origination of the message until it is finally received, right? So this is the definition of first. Okay, then you say, first we do encryption, and then we do fault-tolerant encoding, right? I would argue the same way. I would do it in the same order. Now the question is, why?
Because I feel that if we do the other way around, the encryption are not protected by the fault tolerance code.
Why isn't it practical? It's both error correcting or error tolerating encoding as well as encryption. It's an encoding scheme working on bit strings. So in this sense, I would argue it's practical. In which sense is it not practical? Maybe I help you a little bit, because this is the good idea if you do exercises together here. And if someone started to do it, then of course it makes sense to continue here. We had pictures like this. So we had different encryption schemes. And one property we discussed was error extension. It was a property if only a single bit is transmitted in the wrong way, then this might change many, many bits in a synchronous cipher, it might even change all, meaning half of, the following bits. So what is the relationship to what to do first? So let's assume we do it the other way around. So let's assume we do first error correcting coding and then encryption. What would happen?
So if some errors happen in the transfer, in the decryption,
That is, the encryption would change the characteristics of the channel. For example, maybe if we are talking about a communication channel, if you are very, very lucky, this channel has a property that mainly it's doing single-bit errors. And maybe single-bit errors are independent from other single-bit errors. Now, if we do encryption, a single-bit error is causing many bit errors. So, in some sense, it makes our channel worse. If it's a synchronous cipher, it might make the channel really worse. It could completely break the channel if you don't do reinitialization with the synchronous stream cipher. In any case, putting encryption in a channel is changing the error characteristics of the channel. So if you do error correcting coding, what does it achieve and what has to be taken into consideration in designing error correcting codes? You have to know something about the channel, right? Whether it's single bit errors or whether you have usually burst errors. That is, if one bit is changed, then the bits around that bit are changed as well with large probability. So in some sense, you have to know something about the channel, and then you adapt the coding accordingly. So if you have done that, of course, it would be a completely silly idea to put encryption in between the channel and the error correcting coding. Which, now turning it the other way around, means first we should encrypt, and we can do so under the assumption that in some sense we have a perfect channel. And then the error correcting code which comes next has the duty to transform an imperfect channel into a nearly perfect one. I don't term it a perfect channel. You know that in technology there's nothing like perfection. But of course it should get closer to perfection. Which means that we have to deal with errors much less frequently. Which means, with respect to encryption, that getting partners in sync again should be an operation which very rarely occurs, because it's not needed if the channel works error-free at the level of the encryption. So these are my arguments. So with respect to the architecture, you are fully right. And maybe now it's easier to argue why this is the right way to do it. Okay? Okay. And now we have to discuss how we can change the inner workings of a network to protect who is communicating to whom. If you remember, last week we discussed what kind of protection we can have outside the network. So temporarily decoupling processing and some kind of local selection, these are good ideas and we should use them. But mainly they are insufficient if used alone. So protection inside the network is now the issue we are going to discuss. If I ask you, how would you protect sending or receiving of messages, then I would assume that after a few minutes you come up with the proposal, I can protect reception of messages by just broadcasting messages to everyone. This is probably something you would invent within a few minutes. Yes. This probably is the oldest technique known. Protecting the recipient is conceptually very easy. Just broadcast everything to every station. I didn't say to every person. So this is not a technique of spamming everyone. It's just transmitting the signals, transmitting the messages to each station, and hopefully each station does some kind of filtering, what is interesting to the human being in front of the station. This kind of filtering we will then call addressing. In particular, we call it implicit addressing. Come to that later. If we think about broadcast, first, two remarks. Of course, if you broadcast a message to everyone, either the service should be in a way that the message content may be known to everyone. For example, if you're talking about weather forecast, you could just broadcast all the data of the weather forecast to everyone. Then everyone would know, hopefully, how the weather will develop. Because there's not any, let's say, personal information in a weather forecast. But if you are writing a love letter to your girlfriend, then just broadcasting that letter to everyone, just to keep secret who your girlfriend is, no good idea probably. So what would you do? You would end-to-end encrypt the love letter, and then of course you could broadcast it. And then the broadcast makes sure an outside observer, or everybody except you and your girlfriend, doesn't get any clue who your girlfriend is. And only, this is what end-to-end encryption achieves, and only your girlfriend can read your love letter. So please keep in mind, for many techniques we will discuss in the future, I assume that end-to-end encryption is in place whenever we are dealing with message content which is not public. Second remark, broadcast, I said, is very, very simple conceptually. Implementing it at an affordable price may be not so simple, depending on network topology, on the media you are using. But first, it seems to be conceptually very simple. But if you are talking about security, your broadcast should be secure against your attacker. And a modifying attacker might interfere with the broadcast. For example, making sure that only some stations get the message. And then if a reaction on the message occurs, then it's pretty clear that the recipient is one of those stations which got the message. You know, you can do the game a little bit more clever by just delaying messages, not just shielding messages, but just making sure some stations get messages earlier than other stations. And then, if it's mainly about computer-to-computer communication, for example, you have a kind of encoding scheme that whenever a message arrives, your station sends an acknowledgement. And if these acknowledgements are not done at the broadcast level, but at the semantic level that, oh, I'm the recipient of the message, I should acknowledge. And not, oh, I'm one of the 100,000 people getting the broadcast, though 100,000 people acknowledge the broadcast. If this is not what we are talking about, but an end-to-end acknowledgement, oh, this is a message for me, so let's acknowledge first, and later on read it. So if the acknowledgement is done by your computer, an attacker might know an awful lot about timing. And just delaying a message a few milliseconds may be enough if an acknowledgement is sent automatically. To make a distinction between, hey, is the recipient in this group or which got the message without delay, or in another group which got it with some delay. And of course now you can work with different amounts of delay, and now you have more than two groups. So you see what is conceptually very simple against an attacker which is just an observing attacker gets really tough against a modifying attacker. At least it gets tough in the general case. Of course, if your broadcast network is, for example, a satellite network, that is, you have a geostationary satellite just broadcasting to the whole of Europe, it's really hard for the attacker to interfere with that kind of broadcast selectively. Of course, he could interfere with the broadcast at all. Maybe in the extreme case, shoot down the satellite. But then nobody gets a message. So it's not really serving the purpose of de-anonymizing the recipient. Of course, an attacker could try to isolate people from the satellite. So for example, if I would have some kind of Faraday cage, and I could selectively put you into that Faraday cage, then I could observe what happens. But probably you would find it quite strange if someone is walking around with a mobile Faraday cage and asks you, so please could you get into my cage for a minute and I just do some experiments and want to learn something about network traffic. Okay. Probably, at least I would hope so, you would ask a couple of questions. What's the real purpose of this exercise and whether you are really obliged and willing to participate, right? So in some situations, the medium or the basic communication layer could provide for a reasonably secure broadcast. If so, we are very lucky. If broadcast is implemented by some protocols, then of course an attacker could attack these protocols. And just doing some kind of denial of service attack, or more moderately trying to exhaust some resources, will delay or even delete messages which will not make it to some of the recipients. And this probably is much less obtrusive to people than a mobile Faraday cage, because everyone knows sometimes on the internet you have more traffic than can be handled. So messages are either delayed or skipped. So this happens. I wouldn't call it an attack. It may just happen by the normal use of the internet. Okay. So conceptually, broadcast is very simple. If you really want to have it secure, it may get much more involved. How about performance? It's pretty clear if you have a point-to-point network, no broadcast network, if you start introducing broadcast, the performance of your network will decrease. At least if your service is a point-to-point service. Maybe if you are implementing on a point-to-point network services like TV, implementing broadcast for the TV services wouldn't decrease your performance too much. But if you are implementing point-to-point services by broadcast, then usually your performance, your throughput goes down. In the extreme case, a broadcast to n people costs you n times as much as a point-to-point transmission of your message. So in the worst case, broadcast brings down your performance by a factor of the number of the participants in your network. You can be lucky if you are talking about a satellite network, maybe broadcast doesn't cost you anything. Then you should make good use of this broadcast capability you have in your network. Okay. What we next have to discuss is how does technology develop? Usually, communication networks get ever more powerful. When I was in your situation, when I was a student, having a 2 kilobit per second modem connection to a central computer, this was something which was amazing. My professors at that time were very, very proud that they could interconnect their PDP-11s by 2 kilobit per second digital channels using a modem. Or acoustic coupler, this is what you did as a private citizen. It was 300 bits per second. And this was state of the art. So, okay. In the meantime, I would assume we can do faster than that, right? And I would say astonishingly faster than that. So maybe some services which are modest in their demand of resources, modest compared to the technological level of today, can be implemented using broadcast. For example, if you would say we are going to implement something like the SMS service, short message service of our mobile phones, and we want to do that in a privacy-friendly way, then probably it could be done using broadcast on the internet. If someone comes up and says, hey, I want not only the SMS service to be implemented on the internet using broadcast, I want to broadcast all conversation done via phone on the internet, then I would say, okay, wait a few decades, then do it. Okay, so performance for some services surely is an issue. and for others, probably it isn't anymore. Addressing. As mentioned already, human beings usually don't like broadcast. Let's say for the first 3 love letters I get, which are misrouted to me, I would say, oh, this is a curiosity, maybe I read it, maybe I don't read it. But I'm pretty sure after the 3rd love letter, it gets really boring. I'm not interested in reading love letters addressed to other people. Sorry, maybe I'm not emotional enough, but okay, it's just boring. So whenever we do broadcast, we have to make sure that messages only make it to addresses they should really make it to. Usually, if you are talking about addressing, we are talking about something I will call explicit addressing. Usually, if you talk about addressing, it's about routing, or some people speak it routing. It's the same. I think one is English, one is American tongue. So, usual addresses describe a particular location within the network, be it a geographical location, be it a particular station. And usually routing then, or routing, is a process making sure that the message gets there. So if explicit addresses describe either a place in the network, a physical place, or a station, then probably this is not really a good idea for privacy. Because either it contains the information where the addressee is at the moment, or it contains information what station the addressee is using at the moment, wherever the station might be at the moment. So what you usually learn about addressing has nothing to do with privacy. It's mainly a kind of efficiency improvement over broadcast. Broadcast usually is too expensive, so we do routing. Now I want to introduce addresses which are introduced with the sole purpose of serving privacy, or more precisely, enabling anonymity of the recipient, or as I will argue, even they will enable unobservability of the recipient. Because in the limiting case, you don't know whether the message is received at all. So it's even unobservable whether it's received. And under the assumption it is received, then it should at least be that the recipient can stay anonymous. This kind of address I will call implicit address. So it's the contrary to an explicit address. And implicit addresses you can't use for routing because they don't tell you anything. They are just a kind of attribute for the station of the addressee that this message is addressed to that station. So this station in some sense has to process the message, maybe to decrypt it, maybe to forward it internally to the right service process. Implicit addresses can be split up in 2 variants. One variant is called invisible. That is, if I'm using the same implicit address twice, any observer should be able, or no observer should be able to detect that. That is, reusing implicit addresses should not be detectable. Reusing an address should look the same as if you would use another address. The same with encryption. If you are encrypting the same plain text twice, if you want to be on the safe side, the two ciphertexts you generate should be completely unrelated. This is what we usually achieve by probabilistic encryption. So with invisible implicit addresses, if you are using the same address twice, it should look completely unrelated to everyone except the recipient. Of course, for the recipient, for the intended recipient, it's somehow related, because if you're reusing the address, the same station should pay attention to it. The contrary to invisible is visible. That is, an external observer can make sure, or can test, or verify, okay, the same address is used as in this message as in that message. How to implement that? Invisible addresses can be implemented using an encryption scheme. In the extreme implementation, you would do the following. You would encrypt your plaintext probabilistically. Everybody would try to decrypt. And if an interesting plaintext reappears, then probably this was a message for you. So if I decrypt all messages, and if then a love letter appears, then I can feel very emotional, because obviously this is a letter to me, or at least to the person holding the decryption key. Hopefully then it's me. So encryption can make sure that reuse of the same key for encryption cannot be detected by anybody except the party being able to decrypt. This is what you achieve with probabilistic encryption. Assuming, of course, everybody are using the same security parameters, etc., etc., etc. Same crypto system, for example. Visible implicit addresses could just be random numbers. You could just arrange, if you want to send me something, please pre-append this random number to your message. And then my station mainly needs a kind of memory check, associative memory, in case I have many addresses. And then the associative memory would check in parallel if any of the random numbers I'm waiting for, because they are my addresses, is in front of the message. If so, the message is retained and processed. If not, forwarded to device 0. It's pretty clear that using an associative memory to check for patterns or to check for particular random numbers is much more efficient than decryption. Many orders of magnitude in between. So it's pretty clear that if you are looking for efficiency, invisible addresses are not our first choice. invisible addresses cause cryptographic operations. And if we are talking about broadcast, so we are talking about many, many messages arriving at each station, decrypting them all might get an issue. Surely decryption is not an issue if you are talking about end-to-end encryption, so your station knows what to decrypt. But if your station should decrypt, in the limiting case, all traffic worldwide, then it gets tough for your station. Using visible addresses mainly can be done by having kind of associative memory, or if you don't have hardware support, then maybe if you have 5 addresses, then you're just checking whether one of the 5 patterns is there, and then you copy it. So it's much faster than decryption. Next, we can discuss what kind of implicit addressing could be used in which situation of address distribution. And with address distribution, I mean who knows which addresses. And here I discuss the 2 limiting cases. The first limiting case is addresses are public. Everybody knows all the addresses, all the public addresses. And the other limiting case is an address is private. Private then usually means only 2 people know the address. In communication, it's not terribly useful if only 1 person knows an address, because this means that mainly this person can talk to him or herself. I know that some people like to do that, but usually this is not called communication. At least I wouldn't call it that way. So a private address is known to 2 entities if it's going to be used for communication. If you combine public addresses with invisible, then, as I will show you in a few minutes, what we basically need and what we basically implement is a public key encryption scheme. So if you want a public address to be an invisible implicit address, it boils down to use a public key encryption system. And we can even prove that there's no more efficient way, because the functionality of having a public invisible address can be very easily used to implement a public key encryption system. So these 2 things are equivalent, which of course means there's no hope that you will get public addressing with invisible implicit addresses more efficient than public key cryptography. And you know that public key cryptography is a factor of 1,000 or maybe 10,000 slower than symmetric cryptography. So, to make a long story short, this field here to implement is really expensive. Of course, if you go from public address to private address, it gets less costly. It's equivalent to symmetric encryption, so maybe it's a factor of 1,000 or 10,000 more efficient. If you go to visible, of course, having a visible address which is publicly known doesn't sound really privacy friendly. So probably you shouldn't use that. It's cheap, but still you shouldn't use that. By the way, there may be some services on the internet which are completely free, but still my recommendation would be don't use that. Shouldn't use everything which is cheap or free. If you have a visible implicit address and it's a private address, and if you go to the limiting case that you only use it once, then this sounds like a splendid good idea. If it's only used once, maybe people see it. Maybe people make a recording of it. Maybe people try to evaluate it. But if it's only used once, not much to learn about it. So the idea is, if we want to have a very efficient scheme for private addresses, then it would be a splendid good idea to change the private address after each use. How to do it? Probably it's not really a good idea that after each use you decide, and then I'm going to send a message and telling I'm going to change my address. Because this would be a second message, how to address that. Even if in the original message, okay, this might be an idea, in the original message you reserve some bytes to say each message should contain the next address, or the address to be used next. Okay, but still I would say, hey, this is a waste of bits. If you want two stations to change the visible addresses in the same way, what is the easiest way to implement that? And if you want that the visible addresses are not related to each other, what is the simplest way to do that? After you learned a lot about cryptography, so what to use? Yes, use a pseudo-random generator. And this even would help if a message is lost. If you, in each message, just tell the recipient, and this is the next address I'm going to use. If the message is lost, the connection is broken. If you have a generator, and if you are waiting for some while and nothing happens, or maybe even before that, you are looking for the next versions of the address. So if some messages are lost, it still works. So how to sum up? If somehow we manage to exchange a private address, it really gets fine. The implementation gets very efficient because detecting addresses with an associative memory is cheap. And just replacing the address after each use is very, very affordable. Just use a pseudo-random number generator. So pretty clear what to do if you manage to exchange a private address. So for many situations, I would say this is fine. If you want to communicate with your girlfriend, I assume at least once you did meet in the past, so exchange a private address. If you want to contact a kind of stranger, I don't understand, but some people like to send love letters to complete strangers. Maybe it's funny for me emotionally, but maybe some people like to do that. Okay, sometimes they even need some kind of JPEGs before that, and then they have the feeling they know what the other entity is, but please don't tell them that JPEGs can be copied and distributed quite easily, so you have no clue to whom you are really writing. Okay, so some people write to complete strangers, or more generally, sometimes even I want to get some kind of service or information from an entity I did not communicate with before. So then I have to use a kind of public address, because there was no interaction before. There's no private address still established. And then I would say, okay, I will use an invisible public address, but only one time, only for the first message. And in this message, or as part of this message transfer, I will communicate a private address being used for the answer and all further communication. At least for all further communication, as long as I want to be linkable to my initial message. So if you do some e-commerce, so if you want to buy something, and you first want to get some information, you want to see what Amazon has on offer, without telling Amazon who you are, what you did buy in the past. You just want to start from scratch. Some people like this. Some other people want to buy something they, I would argue, not really need. So if you want to do that, then maybe it's a good idea that Amazon gives you some proposals, what you should buy, depending on your past. Okay, if you don't want to have that, maybe you address your message to Amazon using the public information of Amazon and tell them an address how to contact you, how to send you back the answer. And for one transaction, you of course should keep to that kind of private address. If then in the next transaction you again want to start from scratch, then of course you have to use a public address again. Otherwise, if you are using the private address further for a second transaction, of course Amazon would know, hey, this is the same entity which just did buy this or that, right? So mainly this is the concept of broadcast and how to use it. Do you have questions? Then I should go a little bit more into detail why different kind of implicit addressing schemes are equivalent to what kind of encryption. So as I mentioned, invisible public addresses are equivalent to an asymmetric encryption system. How could we prove that? First, if I want to have equivalence, I have to show you get from left to right and from right to left. So if we have an asymmetric encryption system, it's very straightforward to implement invisible public addresses. Just encrypt the plain text probabilistically and make sure that the plain text has some kind of redundancy, which is checkable by computers. So, for example, you take the plain text, you hash it using a cryptographic hash function, you attach the hash value to the plain text, and then you encrypt the stuff. Then testing for the address means you decrypt using your secret key, you get a bit string, you detach the last part, which hopefully is the hash value, you hash the first part, and if the detached hash value is calculated by your hashing operation, then it's addressed to you. Fine. So pretty clear, if you have an asymmetric encryption system, we can implement invisible public addressing, right? Hopefully clear to everyone. If not, please ask. Now it gets a little bit more tricky, because we have to argue that if we have invisible public addressing, then you can encrypt in a public key scenario. How to do that? Let's assume I want to send you a long message. Assume 1,000 bits. Okay? And I want to make sure that nobody of you understands what message I'm sending. This is encryption, right? So maybe we can talk in public, hey, I want to send you an encrypted message. It's not steganography. It may be public that I'm going to send you a secret message. We could even agree that, hey, I'm going to send you a secret message of 1,000 bits. Okay, length of the message usually is public. And we could even speak up in public how we do that. So I could send you in plain message, hey, I want to send you 1,000 bits. And this is a trick how I do it in secret. I will send you 1,000 messages just to send you 1,000 bits in secret, making sure that each of the messages, each of the 1,000 messages I'm going to send you, either is addressed to you according to the invisible public address, or it's not. If it's addressed to you, then let's define it to be a 1. If it's not addressed to you, then let's define it to be a 0. And then I send you, let's say, an email with 1,000 messages attached. You test one by one whether these messages are addressed to you. If so, you take it as a 1. If not, you take it as a 0. And now, by definition, nobody of you can test whether this is a message addressed to him. Only he can test it. So we have a protocol. Okay, I have to admit somehow it's expensive in the sense that we are wasting bits. Yes, we do. But I can use invisible public addressing to send a secret message in a public key scenario. Okay? So in some sense, we know the two schemes, invisible public addressing and asymmetric encryption systems, are equivalent. If you have one, you can implement the other. I have to admit that efficiency is slightly different. So if you have an asymmetric encryption system, you can quite efficiently implement invisible public addressing. Whereas the scheme I just described, okay, it's not very efficient, but at least for shorter message, I would say it's workable. So in practice, probably, you would again use hybrid encryption. That is, I wouldn't send you 1,000 bits in secret. I would send you a key of, let's say, 128 bits, and then it goes symmetric. And now you see, now it gets really workable. Of course, we can do the same with respect to invisible private addresses and symmetric encryption. Let's assume we have symmetric encryption. And this includes, of course, we have exchanged some key. Otherwise, you haven't symmetric encryption. The crypto system alone doesn't help you. Then it's pretty clear how I send a message to you. I encrypt it. Of course, before doing so, I attach some kind of redundancy, which can be checked by your computer. Maybe again, I hash it in plain text, then I encrypt. Your computer decrypts everything, straps off the hash value, hashes what is remaining and compares it to hash values. If they match, fine. So again, it's very efficient if you have a symmetric encryption system to implement an invisible private addressing scheme. And again, of course, if we have a private addressing scheme, nobody of you understands these addresses, we can do the same trick. We can say it's a 1 if the address matches, it's a 0 if it doesn't match. Okay, so this kind of explanation gives some justification of what I here already assumed, or what I already used for my argumentation, that invisible really somehow is costly and can only be done using schemes which are as expensive as encryption. Because if there would be schemes which are much more efficient than encryption, then I would get more efficient encryption because I could use the addressing scheme for encryption. And in addition, we know public addressing is more expensive than private one, so maybe we use public addressing only for setup purposes. For all other purposes, we will use private addresses, and here, of course, we'll go for visible ones because they are the cheapest ones to be implemented. Okay. Any questions? If not, then I should describe or will describe another technology to protect the recipient of messages. The technology I'm going to describe to you, I would say, I would really be surprised if you would invent it within a year. At least when I was young, when I tried to invent those technologies, it took much longer, and in this case, it wasn't my group which invented it. My group then later on did some improvements, but the basic idea was the idea of another group. So now it gets somehow tricky. I think broadcast was simple. Having the equivalence, okay, between the kinds of addressing and the encryption, okay, I wouldn't say it's really complicated, but okay, it takes some hours, then you have it. But from now on, okay, maybe it gets tricky. What we had is broadcast. This was the technique we had. So maybe we have some broadcaster, we have a bunch of messages, and this broadcaster is going to broadcast to all possible recipients. And hopefully the right recipient receives the message and handles it. The second technique I'm going to discuss now goes the other way around. We have a kind of message services which waits for queries. So it's the recipient who gets active. And now what do we want to protect? We want to protect in which message is the recipient interested. Maybe we cannot protect that this pink guy gets interested in a message because he's going to query the service. And until now, we didn't discuss about sender anonymity. So maybe if this pink guy is just using an ordinary communication network, it's pretty clear this guy is interested in some message. Maybe we try to conceal in which message he really is interested. Now, of course, he could just say, hey, I'm using local selection, so please send me all your messages. And then I select locally. If we do so, what would we get? Broadcast. Implemented in a very expensive way. Because now everybody would ask for all the messages. Maybe at different times. So this would not be efficient. But, and now comes somehow the surprise, but there is a technique that this guy can query the message service asking for a particular message and getting that particular message without the service being able to learn which message is queried. So a straightforward implementation, of course, would be local selection. Please send me all the messages, and then I'm doing my selection locally. This is straightforward, conceptually easy, but too expensive. So can we do better? And the answer is yes, we can do. The basic idea of David Cooper and Kenneth Berman is published in the year 1995. And the idea is that we have a message service which has several servers. So the servers are here, the circles. So in this example, I have 5 servers. And within all these servers, I have the same set of messages. So each server has a local database with the same content. So in some sense, the message service is some kind of replicated database. And now our user will query some or even all of the servers, get the answers, combine the answers, and then get the message he's interested in. For simplicity, and in our example, we just assume that the user knows the number of the message, the position of the message within the database. So he is selecting a message saying, I'm interested in message, what do we do here? 3. He has no clue what the bits of message 3 are. This is what he's going to learn. But let's assume he knows he's interested in message 3. Okay. How does he proceed? He generates, if he decided to query 3 servers in my example, so he selects 3 out of 5 servers, he generates 3 minus 1 being 2 random vectors, random bit strings. And the length of these bit strings here is the number of messages. So for each message, there's a bit position in these bit strings. We'll need that. 2 of them are generated randomly. And maybe these will be the bit strings we are going to forward to X and we are going to forward to Y. Next, the user is going to add up these 2 vectors bit by bit. So 1 plus 1 yields 0, 0 plus 1 yields 1, 0 plus 0 yields 0, and 1 plus 0 yields 1. Bit by bit, mod 2, or XOR if you like. Let's assume this shall be forwarded to Z with a slight modification. If the user is interested in message 3, he's inverting the bit at position 3. So if here is a 0, then here at this position there will be a 1, and vice versa. Now the third vector, which has been calculated using the other vectors and the knowledge which message is to be queried, this is forwarded to the third server. Now I have to define how servers react to the bit strings they get. Each server takes the bit string it gets and does the following. Wherever within the bit string there is a 1, the server takes a corresponding message in his database and adds all those messages up. So server X will add up message 1 and 4. So he's going to add up message 1 and 4. And the adding up is done again bit by bit, mod 2, so XOR. So the answer to the question is message 1 XOR message 4. Same does Y. Y is going to add up message 1 and message 2. And Z has to add up message 2, 3, and 4. So he does. So backwards, we get from here transmitted to the user the sum of message 1 and 4. From server Y to the user, the sum of message 1 and 2. And from Z to the user, the message sum of 2, 3, and 4. Of course, all this end-to-end encrypted. So both the communication from the user to the servers and from the servers to the users are end-to-end encrypted. I don't show that because end-to-end encryption is a concept we all know, and it would only make the notation more complicated. But it has to be end-to-end encrypted. So what does the user do? He gets from the 3 servers queried the answers, and he is just going to add the 3 answers bit by bit, XOR. And now what happens? You see message 1 is cancelling, message 4 is cancelling each other, message 2 is cancelling, and all which is remaining is message 3. Oh, somehow magic, surprise. Why that? And of course the answer is simple. Let's assume we would send this string. What would be the invariant? What would be the miracle? If you add up bit by bit, and then you consider all the vectors, all the 3 vectors, what does it achieve? It achieves that in each position you have an even number of 1s. Why? If you have an even number of 1s already in the random vectors, then the result of your mod 2 operation is a 0, so still you have an even number, right? If you have an uneven number within the random vectors of 1s, then your result is a 1. So overall, it's an even number of 1s. So, and what happens if you are adding an even number of times some bit string to something? Mod 2. It means you can save a lot of labor. Don't add this. It's cancelling. So this is the magic behind it. It's clear? If not, please ask, because this is a basic trick, and the whole scheme is no fun if you don't understand the trick. It's just as a joke where you don't get it, why it's funny. So please ask.
The message service gets all your questions, and it knows which message you're interested in.
Yes. So now you are talking about, hey, now please provide a security analysis. What you just do is this, yes. If we consider the message service as a whole, then of course they get all the information. What would they do? They would just add up the vectors they get, and the sum of all the vectors bit by bit would be a vector where we have at position 3 a 1, and they would know message 3 is a message queried. So in some sense, here with broadcast, we just said it's secure against at least an observing attacker if broadcast happens. You don't need a kind of additional assumption. If broadcast happened, it's secure by definition. Here, it's more complicated. If all the servers cooperate, then obviously it's insecure, as you pointed out. The question is, can we argue, can we prove that if all but one of the servers used cooperate, then it's secure? And here the answer is yes, can be proved. So if all the servers you are querying work against you, you have lost. But now again, I already gave it to you as a motivation in the last term. This lecture could be called security, and including privacy, provided by distributed systems. Not only in distributed systems, but by distributed systems. So the usual trick, let's choose message servers where we have reason to believe that they don't work together against the users. So maybe this server is operated by the Roman Catholic Church. This server is operated, what shall I say, by the left-wing party. Usually they don't have too much in common, maybe except we are in South America, where in some decades they had a lot in common, but okay, at the moment probably they have. A third server may be operated by Mossad, because they don't cooperate with anybody. I'm not sure whether this is true, but if you assume that, then including Mossad would be a very good idea. So, if not all three cooperate, then we have got what we wanted. Of course, if they all cooperate against us, then bad luck. So what do you do if you are paranoid? You would say, hey, why could you be so silly that you could use 5 servers, but you used only 3? This is silly. You should use more servers. In the limiting case, hundreds of thousands of servers. And then I would say you have to be really paranoid to assume that all the rest of the world is working against you. Okay, if this is the case, we cannot really exclude it, then you have a problem. But then I would say you have not only a problem with your privacy, then probably we have a much more fundamental problem. So how would you argue that you only used 3 servers? Because using more servers is more expensive. So somehow you have to balance your security and the expenses you're willing to pay. Sounds strange on the internet. Isn't everything free? Something to pay for resources? Please keep in mind, even if you as a user feel that something is free, someone has to pay for it. For example, if you're using Google services for free, Google has to pay for the services. They have to provide it. They have expenses. So how do you pay Google? By your personal data. They make profit out of it. Otherwise, it wouldn't work out. Okay, so thinking in terms of resources and thinking we shouldn't waste resources, I think should be a general attitude for computer science students, right? There's nothing like a free lunch. This is true if you see the lunch very concretely. If someone invites you for lunch, he wants something from you. And even in cyberspace, there's nothing like a really free service. Usually people have some motivation why they offer that service. So, using more servers is more expensive. Why? We have to query more servers. More servers have to process our queries. We get more answers, and we have to add them up. So what expenses occur? We have more communication. More servers have work. And on the way back, again, we have more communication. And finally, we have to add up more. So these are the expenses. Now, of course, the question is, what is really expensive? And now, of course, it gets tough, because in some sense, expenses, if you think of them in monetary terms, it's a kind of definition. It's not a conclusion. Somehow, expenses are defined. Okay, maybe this is contrast to what you usually think about markets, where you would say the expenses in monetary terms are derived properties. They are something like natural prices, but I'm not a firm believer in natural prices in high tech. If you think about the iPhone, there's nothing like a natural price for the iPhone. Okay. So usually, and now think about what you pay. I've never been charged how many calculations does this device internally. At least this is roughly true. If I do more calculations in this device, how do I pay for that? I have to recharge it earlier. And maybe it's increasing my electricity bill at home a little bit. Often when I used servers, I haven't been charged by using the servers. Some servers are free to use. What I am charged, and this I'm experiencing each day, is in the communication. If this device communicates with another device, not over Bluetooth, okay, there's local communication which they don't charge. At least, maybe Apple is trying to charge that, but at least Sony Ericsson doesn't. So I'm absolutely in favor of the iPhone and the business model behind that. So I did resist the temptation to buy an iPhone. Some people who know me couldn't believe that I resisted buying an iPhone, but okay, this is only a side remark. So what I try to do, and what my research group tried to do, is, can we save expenses? In the limiting case, can we make it affordable to use more servers? And in the best of all cases, using more servers wouldn't make the procedure more expensive. If you could achieve that, then it would be much easier to live your life and staying paranoid, because you could get it more secure without paying for that. So for paranoids, this would be nice. And in some sense, security research is making life more enjoyable for paranoids. Of course, we believe we are right, we are not paranoids, but all the rest of the population, they are somehow naive. Okay. And in some sense, of course, both standpoints have some truth in it. Often, even if a system is insecure, nothing happens. But sometimes it really happens. So, okay. Both groups can argue that, at least to some part, it's true what they believe. So, can we change the scheme to make it more affordable? And what we achieved is, we can bring the communication between the user and the servers. This communication we can, let's say, change in a way that using more servers doesn't cost anything. What we can't do is reducing the workload of the servers. And what we can't do is reducing the workload of the user much. But let's see how to do it. First, we want to replace random bit strings by pseudo-random ones. So this, of course, wouldn't make much use if the bit string is only 4 bits long. But if you have millions or even billions of messages, then making bit strings shorter means there's less to transmit to the servers, which brings my bill I have to pay to my mobile operator down, which I would say this is enjoyable, at least for me. Maybe not for the mobile operator, but for me it's okay. If we do that, that is, here we have not a random bit string, but a pseudo-random one. This changes two properties. First, less bits to communicate to the servers, so this is a plus, this is good. But, of course, it reduces information theoretical security to complexity theoretical security. If you do it randomly, any argument about security would be an argument that an attacker has not enough information to break it. And now, if you do pseudo-random generation of the vectors, then the argument can only be an attacker has not enough computing power to break it. In some sense, of course, still we have to transmit one vector, because I don't know a procedure which, if I'm going to modify something, gives me a very short encoding of that. So this third vector mainly is a random bit string calculated by pseudo-random bit strings and 1 bit modified. So I have no idea and probably there doesn't exist any good coding scheme for that. So one vector has to be transmitted in full length, which mainly means, in my example of 3 servers, what we will have to transmit upstream is roughly 1/3 of the bits we had to do to transmit initially. Next idea is, can we achieve the same? We had mainly to do one transmission upstream. Can we make sure that downstream we don't get 3 messages, but only 1? So in some sense, can we make the servers add the 3 results for the user? Sounds strange, because we said we don't want the servers to get in a position that any server, or at least all but one, can calculate the result. So if you ask them, please add it up, then in some sense, of course, they know the result. So just giving them the plain text and say, please add it up, then we only have to transmit the sum to the user. This wouldn't be a helpful idea, because the result would be the message queried. So the entity doing the adding up would know the message queried. But nevertheless, we can do that if we use a scheme where end-to-end encryption and adding up commute. That is, whether you first add up and then encrypt, or whether you first encrypt and then add up, it's the same. If so, the servers could first each encrypt their result. All the results would be added up. And then the user finally would decrypt. And now the question is, do we have an implementation for this? And the answer is yes, we have. Because the same story of adding up we had with the one-time pad. We could use the one-time pad bit by bit, XOR, or call it addition mod 2. And this would be exactly the same operation as combining the answers. Encryption and superposition of results would be the same. So it's pretty obvious that they commute, because it's the same operation. And this is what I would propose doing. That is, if you want to save expenses, then the end-to-end encryption, which I didn't show in the notation till now because I didn't need it, now is chosen to be the one-time pad, either with a random string, or maybe in case of complexity theoretic security with a pseudo-random string. And then the servers can add the end-to-end encrypted answers to the queries and send only the result to the user. And the user then knows which servers he or she queried, what the corresponding paths have been, and he will just add the paths. And in case of 3 servers, he will add 3 paths, and then he will have the result. So what do we achieve going one step back? We achieve that upstream, we only have to transmit one long vector. So okay, it's a long vector, but only one. That is, whether you are using 2 servers, only one, or 3 or 4 or 5 or 100 servers, or only one, mainly is the same. Because one server gets a long string, and I don't see any way to make that string shorter. But all the others only get a very short one. On the way back, yes, one transmission to the user has to take place. But one transmission. It doesn't depend on how many servers you are using. So we are pretty close that by these modifications, I started to invent in 2001, we make our mechanism independent of the number of servers we are using. Of course, the servers have to be there and do their calculations. They need power, etc., etc. So the work for servers doesn't get easier. For the user, again, he has to do some calculations. For each server used, he has to do the end-to-end decryption. But in communication, no change. And of course, if I said for end-to-end encryption, we did arrange with the servers which kind of bit string is used or which pseudo-random string is used. Of course, we could even for these vectors do some kind of pre-arrangement. And then this, which was roughly 1/3, now it gets exactly 1/3. So we can bring down the expense to the expense for one server with respect to the communication here. So this is mainly the improvement we achieved. Do you have questions?
If one server gets only a pseudo-random number as a request, the server knows this.
Yes. So it's public information how many servers you are using.
Yeah, but now the server knows which messages I don't want. Because if he gets an unmodified
No.
Hmm.
Maybe we should talk a little bit about the security argument. It's pretty clear that X and Y, because this is random, don't get any information which message is queried. Right?
Hmm.
So if you do this kind of encoding scheme, it's only Z which might get some information, because here we are changing a bit, or the other stuff is random. But now, if you look at the math, everything is symmetric in the sense that, of course, you could start with this vector and that vector, then add it up, change the third bit, and then you would end up with this vector. So it's completely symmetric. That is, as long as you only have one vector less than all the vectors, you haven't any channel information which message is queried.
Yeah, so then maybe I didn't understand your optimization of the upstream. Can you repeat?
The optimization of the upstream was that this is not random but pseudo-random. This is not random but pseudo-random. So no need to transmit it, because I could just arrange with the server X and Y which pseudo-random bit string to use.
Yeah, but nowadays, if you tell the server which pseudo-random bit string to use, he knows that none of the messages requested by the pseudo-random bit string is of your interest, because else you would.
No. Using. Okay. In this example, but this is only by chance, at position 3 we have a 0 here and a 0 here. So in some sense, okay, maybe even this is a good example. If you look at the bit positions, X and Y could argue we don't touch message 3. And so maybe this is not the message being queried. But so in other words, what is the bit pattern here and how it will be used in the final summing up only gets relevant if you know the last value. Before that, the bit pattern here and there doesn't tell anything. So maybe this is the point. Okay, questions? Okay, then I think we make a break now, and in 20 minutes we continue. During the break, I got one question. Hopefully, this will trigger more questions. The question was, hey, if you say this is roughly 1/3 upstream, what's the difference between 1/3 and roughly 1/3? And here the difference is we are encoding these two vectors as pseudo-random bit strings. That is, what we have to transmit is a short string, a shorter string, just being the initialization of a pseudo-random bitstream generator. And then later on, here I argued now it's precisely 1/3. And the question was, hey, how do you arrive at this? And the answer was, here in this step, we did a new initialization of the pseudo-random generators for each query. And of course, we could avoid this expense in the second, in the third, and the fourth query by just reusing the initially exchanged set of parameters. That is, if I already did arrange with a server a pseudo-random generator, then for the next query, I'm just using the next part of the pseudo-randomly generated bit stream. And this is the way I get rid of the roughly 1/3. I get to precisely 1/3. Okay. So far the question I got. I hope there are more questions, because usually the added value of meeting together in one room is that it's now pretty easy to ask questions and hopefully to get answers. Any more questions? Okay. If not, then I just continue. So until here, what do we have? We have a scheme where if the user querying knows the number of the message he is interested in. He can query it from many, many, many servers without incurring too much communication. Without incurring too much communication to his end device. And usually, if you think about of the expenses of communication, usually communication on the last mile is the expensive part of the communication. It's particularly expensive. It's about mobile services. Usually, communication within the core network, if you do think of cost in terms of bits transmitted, it's much, much cheaper than on the last mile. So mainly, we can use many, many servers without incurring too much communication cost. So this is what we have at the moment. And now, of course, sooner or later, we have to discuss how does the user manage to know in which message he's interested in? How does he get to know the number of the message he is interested in? Okay, so keep that in mind. This will be a question we have to answer, because this scheme assumes the user knows which message to query. Before we get to answer that question, I will show you a second trick my group invented. And the trick is that, of course, if you don't want to get a single message, but if you want to get the XOR of several messages, then it's easy how you do it. You don't invert just one bit, but you invert all the corresponding bits corresponding to the messages, the sum of which you want to get. At the moment, this sounds strange, because why should I be interested in getting the sum of some messages? What's the added value of getting that? But stay tuned, we'll get to that later. So how to do it? So for example, if I want to get the sum of message 2 and message 3, so I'm going to invert the second bit as well. And then is what I get. So message 2 isn't superposed here anymore. And in the result, we get message 2 and message 3. Everything stays unchanged. So, okay, there's a possibility. And of course, this doesn't change anything with respect to keeping secret in which messages the user is interested in. Because whether he is changing one bit or several, it doesn't matter. If you're changing some bits in a random string, the result still is random. And it's only if you take all the strings, all the bit strings together, that you could see the difference. Okay. And now I try to approach the problem how the user knows which message to query. First, going back in the basic scheme, we could of course say, if we have a database of, let's say, 1 million messages, you could say this 1 million messages means just 1 million addressees. So a position in the database could be a kind of implicit address. So if you want to send an address, a message to an address, you just make sure that the corresponding message in the database is replaced by the new message. In the simplest way, it's just overwritten. But keep in mind, we have a special trick, and maybe overwriting a message is not the most efficient way to communicate. And of course, if we are overwriting a message, or if we are replacing a message in the database, then of course this has to be done on all servers. On all servers at the same time. Because if you would have a query when you did already the update in some of the servers and in others you didn't, then surprise, surprise, the result would be inconsistent you get as a user. So, starting from this very basic conception that maybe a place in the database may be a kind of address. We now do it step by step. So in some sense, we could in the database define memory cells, that is a certain place in the database, and more particularly rewritable memory cells as a kind of implicit address. And what the trick now is that I would say rewriting a memory cell, I would not do in just replacing the value, replacing the old value by the new value, or as we call it in computer jargon, just overwriting the old value. I would say it's more clever to overwrite in some sense, to replace by just doing an addition mod 2. That is, if a new value arrives, the new value is added up mod 2, bit by bit, to the old value. And as I did right here, this will, as we shall see, enable to read many cells in one step. But before we get this improvement, probably first we have to think, if we define replacing as adding up mod 2, how can we read? And of course now you can only read the new value, you can read the delta, you can read the difference only if you know the old value. If you know the old value, if you read the new value, it's pretty clear what's the value of the message which arrived in the meantime. It's a difference, so you add it up. So, if we make sure that a station knows locally what the old values have been, if one value is changed by adding up the new message to the old value, and if the station manages to query the new value, it can calculate the value of the message. Clear, hopefully. Right? And now comes the trick. As I mentioned here, a station can query in one step the sum of several messages. Right? This is what we did. One step, and you get the sum of several messages. Now we said a message here corresponds to an implicit address. Now let's assume a user has many implicit addresses. Then of course, if you have no better idea, what does he have to do? He has to create all his addresses one after one. Which means if a user has 1,000 addresses, then he has to do 1,000 queries after each potential update of the database, just to check whether in one of his address boxes a message arrived, right? And 1,000 steps doesn't sound pretty nice. The question is, can we do better? Can we reduce it to one step? And now, if we define rewriting as addition mod 2, this is pretty straightforward. As we mentioned, within one query step, you can query the sum of all your memory cells. And then after a potential update, if again you query the sum of all your memory cells, then it's either the same as the last one. In this case, no message arrived. Or if a message arrived, the difference between the sum of all your memory cells, old and new, the difference between the two is just the message which arrived. So instead of querying one after the other all your memory cells, you just do it in one step, which for me sounds much more clever. And I would say it's much more enjoyable. So with this trick that rewriting is not just done by replacing something, but adding up. So having the delta. This gives us an opportunity to read arbitrary many cells concurrently. The optimistic approach is, of course, admit some kind of concurrency. And this is fine as long as if it goes wrong, it's detected. And it's catched by some other mechanism. So this was my approach of retransmit. And now, how to argue that my modification in this optimistic approach does only make it better and not worse. And I would argue in the way that, let's assume I have 1,000 cells. Then without the optimization, it will take me 1,000 steps to query all my cells. Of course, if two messages arrived, and if they are at different cells, it will work fine if I query one after one. But I would argue that if I can only read each cell after 1,000 steps, then the probability that two collides will be larger than if I can read all the 1,000 cells after each step. So now you need some kind of performance analysis to really compare the two approaches. This kind of analysis I never did, because now you need some kind of queuing theory, some kind of, okay, so ask Mr. Schill or Mr. Rose, and maybe if someone has really fun in stochastics, then this would be a nice work. To the best of my knowing, nobody did it till now. But this would be interesting. And you are right, yes, to make a really strong statement, this has to be figured out, yes. Okay. More questions. I enjoy questions. It's really nice to get questions. Okay, then I assume the basic trick is understood. And as we now pointed out, there's nothing like a free lunch. So even a good trick, it has some price. And okay, if 2 messages arrive, we have a problem. If you're talking about addresses, of course we should ask, can we use channel switching? For computer scientists today, it's a quite natural thing. Each message should have his or its address. In former times, it was different. You did establish a channel, you did it once, and then you had the channel without further addressing as long as you needed it. And only when it was sure that you didn't need it anymore, you did close the channel. So a very old trick is to avoid addressing expenses to switch channels. Or what is much related is to open up a connection. So can we, using this trick, establish channels? And the answer is yes, sure. If in some sense I'm asking fast enough the sum of all my cells, if someone is sending regularly to me, it works fine, as long as I'm querying fast enough. Of course, if I'm too late, then I have lost some data. So, coming back to implicit addresses. In some sense, when I started how this kind of message service, or as I call it, query and superpose, can be used, I started with the feeling that, okay, let's implement implicit addresses there. So we had implicit addresses here, and I hope we have understood it. At least when I came first across querying and superpose, I had the feeling I have really a good understanding of implicit addresses. So I tried to apply it here as well. But in some sense, it didn't work out quite well. It worked out somehow, but not really well. So after a while, I had the feeling that if you are talking about a broadcast, implicit addresses only have to do with efficiency. Why? Because in broadcast, implicit addresses only have value if their evaluation is faster than processing the whole message. So it's only kind of efficiency improvement. With query and superpose, with this kind of message service we are just talking about, implicit addresses have 2 purposes. One is medium access control. That is, we want to make sure that not the same cell is used by different people concurrently, just to avoid overwriting. Or at least, if this is a risk, we have to query fast enough. And then, of course, again, we have an efficiency issue. implicit addressing should reduce the number of messages to be read. If you read all messages, then again it's worse than broadcast. So if we talk about fixed memory cells, this is the impression I gave you here, that a user has a fixed set of cells, then he may query them in one step. So if we have a fixed memory cell, this is mainly a visible implicit address. I can just tell you, hey, if you want to send me a message, please address it to cell, for example, 3. And then I read cell 3 regularly. And maybe I tell you, if you want to send me something, cell 3, cell 15, cell 13, so okay, and then can read it in one step. If we implement that, in some sense, I don't have any need for upstream. So this means, this arrow means upstream, this arrow means downstream. So upstream, we have 0. Because if I'm reading the same cells all the time, no need to do any update. So upstream is 0. Downstream, of course, it's 1. I'm reading n cells, and what I get is, in each time slice, 1 value. So far, sounds good. But the problem is that the number of our addresses is linear in the expense of superposing. Usually what we have with addresses is that your address space grows exponential with the expense. So if you have a linear growth in the length of your addresses, the number of your addresses grows exponentially. So here we have an effect which is extremely nasty. If you want to have twice as many addresses, it just does not mean add an additional bit, but it means that each of the server has twice as much of work, which is not really nice. Okay, so far I would say I'm pretty sure what I'm talking about. And now we get very close to where research might start. I didn't have any student till now who really did a good work or did a thorough analysis about addressing with this kind of message service. So first ideas, but it's not really worked out. If an address here only is linear, the growth of the address space only is linear in the expense, how could we modify? And we could try to say an address is a set of rewritable memory cells, not a single cell, but a set of cells. So message M then is stored in a set of memory cells by choosing, if the cell size is A, choosing A-1 values randomly and choosing the value of the 8th cell such that the sum of all A cells is M. If we do that, of course, if we have n memory cells, then we have many, many, many sets. We have 2 to the power of n subsets, And of course, the empty set is not really a useful variant for information transmission because there's no influence if you have the empty set. So mainly we have an address space of 2 to the n minus 1. But now addresses, meaning sets of rewritable memory cells, overlap. So if you are addressing one address, if it overlaps with another address, it might interfere. Of course, what we can do is, let's be optimistic, hope that it doesn't occur too often, and if it occurs, then retransmit. But of course, whether this is, on average, a good strategy or a bad strategy still has to be found out. I don't know. So this calls for some kind of analysis, which isn't done. You will often see in this kind or this part of the lecture, because now I'm mainly doing lecturing about stuff I did myself, or my group and I did together, we'll come across many, many questions where I can say, hey, nobody on the earth knows that, which usually is a good starting point for your work. So, how to work with the problem that basically we have an address space which is linear in the expanse. What to do about it? First ideas, but not really a solution where we have an analysis whether this is a solution, whether this is an improvement, or it's only making things worse. I don't know. Until now, with the message servers, I mainly talked about public implicit addresses, or let's say more precisely, visible implicit addresses. Why? It was pretty clear whether you are addressing the same memory cell, yes or no. So it's visible. Addresses are visible. It's just the cells. So the question is, with a message service, with query and superpose, is there something like invisible implicit addresses? In some sense, I would argue no, that it isn't. And on the other hand, maybe we can invent something which gets close. And the idea I had, but again it's lacking thorough analysis, could we have something that hopping between different memory cells, that this is kind of invisible implicit addressing? So till now, if you wanted to address the same person, or more precisely the same address, you had to make sure that your message goes into the same cell. Now here, for invisible implicit addressing, it would mean in a different time frame, it has to go to a different cell. And of course, the sender has to know in which cell it has to be sent. And of course, the recipient should be able to know which cell to read as well. How could this be provided? And again, I'm only talking about first ideas, and if someone really gets curious and wants to do work on it, it might be a good idea. So first idea is, the user who wants to use invisible implicit addresses at time t reads the values from reserved memory cells at time t minus 1. And the values in these reserved memory cells at time t minus 1, these values identify the memory cell to be used at time t. So in some sense, our addressing scheme gets indirect. In order to know what to do at time t, we have to read out some values at time t minus 1. Of course, an attacker could do that as well. He could read out those values. So what advantage could the good guys have against the bad guy? Or if you are more general, the bad guys, because we don't know whether it's only one attacker. The advantage I see is if you know at time t minus 1 to whom you want to address at time t, then you know exactly what you want to read in the time slice before. If somehow reading is limited in the sense that nobody can read everything, then the sender has some kind of advantage against the attacker, because the sender knows in advance what to read. And the attacker, if you want to be on the safe side, has to read everything. Or if he only managed to read parts of it, then he has to be lucky to know in the next time slice what is the meaning of which cell. So, how we might implement that? The owner of an address gives each server S a pseudo-random bitstream generator. Each server S replaces at each time step T the contents of its reserved memory cells with the values of the value of the PBG. And then the address, and then this is stored, this value, under this address. And the user queries using another technique we will learn later, maybe not later today, but next week or a few weeks later. We are so-called mixes. Some values of the PBGs, and this is again possible in one step. And then the user employs these values to query and to get an answer. The address owner generates this, reads using query and superpose that, and he calculates the difference for all his invisible implicit addresses together. So this has one message upstream, two messages downstream. And such addresses are insofar invisible that at each point of time only a very little fraction of all possible combinations of the cells are readable to an attacker. So this is one sketch how one might try to achieve it. So please don't be worried. Surely this page or this slide is nothing I will ever ask in any oral examination, because it's just not finished. So this is just a sketch. If someone really gets interested and wants to start work of his or her own in this area. Okay, to sum up. So hopping between memory cells might be close to invisible implicit addresses. And of course, now you can ask yourself, can we extend that to hopping between sets of memory cells? Because then we have a much larger address space if we are considering sets. But again, I don't know any analysis. So what did we do? I would assume you have understood the basic scheme and some performance improvements. You got the trick that if we define an implicit address as a memory cell, then the trick reading memory cells in parallel may be a good one. And then somehow you take notice that getting a clear structure of implicit addressing and this message service is work in progress. It's not done yet. It's unclear. But there are some first ideas, but not really worked out. So far clear? Or any questions or remarks from your side? Okay. Whenever we are talking about mechanisms to protect sender or recipient, or later on we'll see the relationship between sender and recipient, we have to talk in some sense about fault tolerance. Why? Because the mechanisms for providing sender or recipient anonymity make errors, I would say, either more probable or more devastating, more serious. Just go back. If I'm querying as a user a single server, okay, if the server breaks down, I don't get my answer. But if this server is okay, I get my answer. If I want to query several servers, I have to assume that all these servers are up and running. Otherwise, I can't make use of the partial answers I got. Now if you are talking about not only permanent errors, but transient errors, maybe if you're asking a server, you get an answer. And maybe in each, let's say, step 1 in a billion, the answer you get is wrong. Now, if you are querying instead of one server, several, it's enough that in one of the servers an error occurred to make the overall answer you get probably unusable. So in some sense, anonymity usually is constructed in a way that instead of one station, you are using several ones. Security and anonymity gets better because all the several stations have to work against you to de-anonymize or to trace which message is queried. But availability of the service is only given if all servers cooperate, if all the stations work perfectly. Therefore, discussing about fault tolerance is an issue. It has to be done. Because it's nonsense saying, hey, let's make the system more complicated to get better privacy and not discuss how you keep this more complicated, which decreases availability, somehow under control. Because privacy is a nice thing to have, But if your service quality gets too low, then nobody will use it anymore. Okay, so fault tolerance is an issue. And what is often related is that it's, in some cases, not enough to discuss about faults, which might occur by chance. But it may be even possible that an attacker launches a modifying attack. Maybe by just pretending that a fault occurred. So how to deal with this? What to do if the server does not respond, or what to do if the server delivers a wrong response. So let's first discuss case 1. If the server does not respond, it's pretty easy. You submit the same query vector to another server. No need to generate a new query vector. No need to just throw away what you got from the other servers. You just generate a new message with the same query vector to another server and send it. What's the price you pay besides sending another message? That, of course, 2 servers know this query vector. So this decreases the strength of your attacker model a little bit. But again, if you want to get better availability, there's nothing like a free lunch. So you pay for your better availability usually by slightly decreased anonymity. Let's discuss the second issue, what to do if a server delivers a wrong response. First, whenever we are talking about errors or even attacks, what do we need to do? We have to figure out, for example, for a message, has this message really been sent? So a very basic mechanism is, if you want to figure out what went wrong, make sure you know who did send what. And it's pretty clear that this information is authentic. So the usual mechanisms are digitally signed messages, just making sure, under the assumption that the digital signature system is secure, that you can figure out who did send the message and that the message hasn't been modified. So messages should be authenticated so the user can check their integrity and thereby detect whether at least one server did deliver a wrong response. So if the user queries several servers, he gets the answers, he checks the signatures, and then he adds up the answers. And if the outcome is just garbage, then he knows at least one server did not answer correctly. Now he has signatures of different servers. And now he could query or send the same query to a different server, get a signed answer, and compare whether this is really the same result. If not, one of the 2 servers is lying. So this is what we would do if we want to figure out which server did give a wrong answer. So I did continue here. So if something was wrong, use a disjoint set of servers. Of course, you can do it again, not tracing who did misbehave, but just going to a disjoint set of servers. Or you lay traps by sending the same query vector over to many servers and checking their responses by comparison. So here I'm talking about to lay traps. Why I'm talking about traps? Why I'm not talking about usual messages? If a server gives you a wrong answer, and if you now try to find out what really happened, you have to be careful that in this procedure, the information you want to get protected, in this case, in which message are you really interested? This information you want to protect shouldn't get apparent in the procedure in which you've tried to find out what happened. So the basic or the fundamental issue here is only investigate details, what went wrong, if the message you just tried to query or send or whatever you just did, what you wanted to get protected, is not really important to you, not really important to your privacy. And this kind of not important messages for your privacy, I will call trap, laying a trap, because this you can investigate. If the message, if the secret you want to protect is very valuable for you, then probably don't investigate. Then probably do something like asking the same query with a disjoint set of servers and hoping to get the result, getting the answer this time. And this again will be a kind of, how should I say it, a kind of distinction, a kind of valuation we'll come across many times. When you really make sure in a distributed system that a detailed investigation happens, usually this will give a lot of information to other entities. So either you should know in the very beginning what you are doing and what information is being given to others, and making sure that no sensitive information of yours will make it into the investigation, or take the more fundamentalistic approach saying that I will never initiate investigation, or I never will agree to an investigation if information, sensitive information, information whose confidentiality is to be protected, could get involved. So the distinction between, are we talking about a trap and investigating this, or are we talking about investigating a valuable, a genuine message, this distinction is basic. And if you don't lay traps, or if in this case you haven't laid a trap, only way is retry. And if you have no particular suspicion who did misbehave, then probably the best you can do in your retry is avoid everyone you used in your try before. Okay. Any questions so far? Let's see how many minutes we have left. 20 minutes? Okay. So far, we did discuss how to protect the recipient. Why did we start this way? I would argue because broadcast was so easy. It was a good way to start with. I have to admit that talking about this message servers, this was somehow involved. Okay. If we can protect recipients, for some services this is fine. For example, for TV and radio, it would be completely okay if you could protect the recipient. Because the sender, okay, it's not really to be protected. If I'm watching a second German TV program that it's sent by ZDF, this is not really a secret. And I would argue it shouldn't be a secret, it should be public. Everybody should know who generates this TV stream. But on the other hand, I would say ZDF and even the Ministry of the Interior in Germany shouldn't know who in Germany watches which TV stream when. Because this gives an awful amount of information about people. Do I switch the TV stream when it gets violent? Or do I switch it when there's no violence? It tells a lot about my feelings and, okay, so you see? For some services, protecting the recipient is fine, is okay, is all we need. But for many, 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 many services, just sending the recipient is not enough. For all interactive services, even if I fully protect the recipient, if I can trace the senders, and if the role sending and receiving is changed in each step, then either you can protect the sender as well, or protecting the recipient is really void. Okay, so how to protect the sender of a message? The first idea, and again I would assume after 1 minute you would come across it, is to say, hey, I'm going to protect the sender by just making sure dummy traffic is sent, or dummy messages. That is, if I can send messages, if I have nothing to send, if I have some resources left, I will send some messages. To whom? It depends. Maybe I'm addressing that to some particular station, something like a digital waste paper basket, which just has the role of throwing away the messages. Maybe I'm addressing it to the Prime Minister, because I know nobody will read it there anyhow, so I avoid the service of a waste paper basket. If I have some politicians with email addresses, so it depends. What do I put into dummy messages? It could just be random data. In Germany, I would say this is fine. For random data, nobody will care. In some countries, random data too close to encryption. So if you address random data to some authorities, maybe some guys will show up and asking you questions intensively about the meaning of these random data. So it depends. So what is a good strategy for dummy traffic in one country? Maybe not a very clever strategy in another country. But the bottom line is, dummy traffic means you're sending stuff to people or machines, even then, and even to those you don't care. Why do you do that? To conceal against an eavesdropper, someone tapping your communication, to whom you are really communicating. So if you're communicating to other guys, okay. And to conceal when you really are communicating. Because when you are communicating, usually tells me something about your private life. Okay, so far the concept of dummy traffic, which if you look in the usual literature about computer networks and about how to conceal traffic data, usually dummy traffic will be the only mechanism you will find in the literature. What are the limits of dummy traffic? If you send me a message which is really interesting, so I don't have the feeling that it's a random message, if this message is somehow personal, so it's really either telling something about me and maybe in combination with telling something about you, then I'm pretty sure that this is not dummy traffic, that you really communicate with me. And usually, if you're using a normal communication network, in looking at the explicit addresses, I know who you are. Okay, let's discuss that a little bit. If you just get an IP address, I know your IP address. Sometimes I don't know who you are. But if it's a static IP address, if we communicate over and over again, probably after some number of interactions, I will accumulate enough information to really know who you are. If I'm kind of global observer, it gets even more easier. If someone uses an IP address to communicate with me, with my brother, with my social network, and if I do some kind of analysis at that level, after some time it's pretty clear who's who and what the relationship between people are. You find on the internet lots of paper about this stuff. So, okay, maybe in the very beginning, an IP address may be non-personal data. But if it's static, if it's attached to a person for a longer time span or for many transactions, then at least it gets risky. Even without any kind of data retention, stuff like this. Of course, if you have data retention, if you are asking ISPs to divulge identities to IP addresses, okay. There are many ways to get information about the relationship between IP addresses and people if you do it at the legal organizational level. But even without that, just if it's static enough, if an IP address is used for more than one transaction, then it gets a problem. And this is not only IP addresses, it would be MAC addresses, it would be everything, which is a kind of attribute which is stable across several transactions. By the way, your browser configuration. What is the initial size of your browser window? What are the settings of your browser, etc., etc. Everything which is pretty static helps to link different things you do. And this undermines, sooner or later, your anonymity. So, dummy traffic, of course, doesn't protect against the addressee of meaningful messages, by definition not. And maybe dummy traffic makes the protection of the recipient more inefficient. Let's assume every message shall be broadcast to everyone. Then if I want to make no distinction between dummy messages and normal messages, and if I want to use dummy messages to mislead an observer, then if normal messages are broadcast, then dummy traffic should be broadcast as well. Otherwise, it's pretty easy for an observer to sort out what is real traffic and what is dummy traffic. And of course, if I'm broadcast already is expensive, and if I'm broadcasting dummy traffic in addition, then probably it's not the most clever strategy. So I would say it's good to know that in some situation dummy traffic helps a bit, but usually not much, and often it makes other things even worse. So what to do? And this is now pretty close to the situation which brought me into this field. I came into this field in 1983. 1983 was the year in Germany where they planned a census. We had a kind of movement in the normal population against the census, and then later in December, this famous ruling which coined the term informational self-determination. So 1983, we had early versions of the Ethernet. We had early versions of the token ring network of IBM. It was pretty clear that local networks, local area networks were important, mainly because for long-haul networks, the telcos had a monopoly, so you couldn't get powerful long-haul connections at reasonable prices. Therefore, local networks were of more importance than today. Today, even within this building, from time to time, are using GSM technology just to query the internet, because if a server breaks down or whatever, I'm just too lazy to switch between the configurations on my laptop. Okay, so at that time, local area networks were just being invented. They got into the market. It was important. And maybe to understand what I'm telling next, this is a situation to have in mind. So in 1983, I did sit down and said, hey, can we use, for example, local area networks to make sure that instead of sending dummy traffic, because local area networks share some medium, my dummy traffic, or something which looks like dummy traffic originating from me, in reality is useful traffic of other users. Or putting it the other way around, maybe more intuitive, that if I'm sharing a medium between many users, can we arrange it in a way that what the other users send is some kind of cover traffic for each single user. So in a local area network, an attacker can observe what overall is sent on the network, but not observing who sends it. And in some sense, yes, this could be done. And at that time, I thought about different variants. And one I'm going to present to you now is that I thought about ring networks. This will be the topology to discuss next, inspired, of course, by the IBM token ring network. And the attacker model I had in mind gives the headline I gave to it. So unobservability of neighboring lines. That is, I assume that an attacker is not able to tap too many lines. And I assumed we will have something like digital signal regeneration. I'll come to this in a minute. So this was the idea. We have a ring network. We have, in the simplest case, two stations, station 1 and station 2. I want to protect which of the two is sending. Of course, if this is a unidirectional ring, if we would have an attacker here, he could see. If it comes downstream the ring, then it's from station 1. Otherwise, it's from station 2. But if you don't have an attacking station between the two stations, then there is some kind of hope that even if the attacker, this is the station with the black sole, is in front of the two and after, even then he cannot figure out which of the two stations is sending. And of course, it should generalize that if he observes 2, 3, 4 stations in a row, he should not be able to figure out which of the 3, 4, 5 stations is sending. Digital signal regeneration, what does it mean? Let's take the perspective of the attacker. This attacker gets some kind of signal here. It's very reasonable to assume that the attacker here is not only getting bits, but he will get an analog signal. Because on your channel, it's not single bits traveling from here to there, but it's an analog signal being transmitted and being resampled to bits at the receiving station. But a signal arrives, an analog signal, which usually carries different kinds of information. For example, the amplitude may tell you something about the power level here. The dispersion, that is how round everything is, will tell you something about the medium and the distance. So surely it's clear that an attacker here gets more information than just the bits. And now digital signal regeneration means that the signal which arrives here is the same. It's the same signal at the analog level, whether the bits originate from station 2 or it's transmitted from station 1. That is, the two differences which are important for station 2 shouldn't have any influence on the signal. This means digital signal regeneration. That is, the signal here is regenerated. That is, any modification, any analog disturbances here don't make it in that signal. How to implement that? That's conceptually simple. Whatever arrives here is received and resampled, usually written into a buffer. And then it's the same kind of buffer, whether that came from here or there, it's transmitted again. So the attacker here surely has information. My analog signals come from this station, that's pretty clear. Usually, if you are publishing the network topology, it's part of the network topology, it's published. And the additional property of digital signal regeneration makes sure that the shape of signals are the same whether this is the originator or that. Is this realistic? First, it's pretty clear we could build that. Just receive the bits, write it into storage, and then resend it. Is this done? Often not. Why not? Because the delay in those stations should be very small. It's not a good idea to receive 1,000 bits or even more, store it, and then send it. Often this is built in a way that within a station we should have 1 bit delay at most. And then it gets tricky with digital signal regeneration. Maybe this is the right moment to say, okay, we'll continue there.